Good afternoon. Thank you for being here and thanks to the organizers for putting this conference together. My name is Georg Muntingh. I am a senior research scientist at SINTEF Digital in Oslo. I will talk about machine learning for shape reconstruction with a focus on reconstructing heart models from CT scans. This is joint work with Ivar and Oliver at SINTEF as well as Rajan from Rikshospitalet. Now, if you're attending this talk, that means you're missing out on a great parallel talk by our PhD student, Arthur Bezins, on reinforcement learning for social distancing. These talks will be available online after the conference, so I hope you will check out this talk as well. Compared to, for instance, image classification, shape reconstruction is a harder machine learning problem, because creation requires a deeper understanding of the underlying geometric nature of a dataset. I should stress that I use the word understanding very loosely here. I mean it in the sense that a machine learning method can pick up on the underlying geometric essence of a dataset, at least when it is shown enough examples. But in many occasions, it doesn't have to discover this, as we have expert knowledge of this available beforehand. So for instance, blood vessels are continuous, even smooth, and if you know this, it can be a good idea to incorporate this straight into the machine learning method. This is called a smoothness prior. We develop a method that incorporates such a smoothness prior by generating an output shape using geometric representation that has these desired smoothness properties built in. Let's take a look at this representation. At SINTEF and the University of Oslo, research into splines started out way back in the 60s, with a focus on the shipbuilding industry. This image shows the draftman spline, which creates a spline curve passing through fixed points held in place using these heavy weights, which are called ducks, because that's kind of what they look like. It has the property of minimizing the total bending energy, which is desirable for wooden planks forming the hull of a ship. Mathematically, splines are piecewise polynomials, meaning that they're polynomials in different regions of space. And while these polynomials are different, they are tied together with a prescribed smoothness. In this sense, searching for splines with a given smoothness adds a smoothness prior to the space of all shapes. But we are not using spline curves, but spline surfaces. These surfaces are used implicitly, meaning that their intersection with the zero plane gives you the boundary of the generated shapes. There are a couple of advantages. First, we can represent complex and unknown topologies. Second, using splines we can make compact but accurate representations whenever the boundary is smooth, and third, it is easy and efficient to check whether a point belongs to our segmentation, simply by evaluating the spline. Back to the reconstruction problem. We divide it in two parts. First, binary segmentation of each slice, and second, piecing these together in a 3D model. In binary segmentation, we have a single class of interest. In the image, this is the blood pool. And we need to figure out which part of the image are inside or outside this class, resulting in a mask. Our method uses deep learning and takes a CT slice as input and creates a binary mask as output, telling us which pixels belong to our class and which don't. There are two steps. The first is to generate a neural network that provides spline coefficients as output. These coefficients define the implicit spline representation. The second step is to evaluate the spline at the pixel values and apply thresholding to determine the pixels that belong to the given class. The spline coefficients themselves provide a nice smooth representation of the segmentation, but for comparing to existing methods, we sample back at the original input resolution. So for those of you who have a background in machine learning, I'd just like to give a couple of details about our neural network architectures. If you do not have this background, just ignore this and just spend a minute in your happy place. So our initial approach was a very simple, fully convolutional network that was defined by truncating VGG16, which is a well-known network for classification. In our case, we truncated all the fully connected layers and some of the convolutional layers to get a desired output resolution of 1/4 of the input resolution. The second approach was very similar, but we truncated the network less, resulting in a deeper network that provides output coefficients at 1/8 of the resolution of the input. One issue with both these VGG-style networks is that they are very restricted in terms of their output resolution. Another issue is the slightly counterintuitive fact that on contractive networks like these, lower resolution outputs require larger networks. To resolve these issues, we also adapted another well-known network known as the unet. This allows for more freedom over the output resolution. This is achieved by using several applications of adaptive average pooling layers on the skip connections. These layers standardize the size of everything from the bottleneck onwards, meaning that the output resolution is completely independent of the input resolution. Here we can also adjust the depth of the network to give it more or less expressiveness depending on the memory capacity of the hardware. So in order to train these neural networks, we have to define a loss function that compares the output of our network with the ground truth data. The issue we have here is that the network outputs spline coefficients, while the ground truth data are manually labeled high resolution binary images. We solve this by performing spline evaluation as part of the loss function, but do it in a differentiable way. So we used a total of 66 CT volumes in our work for training, validation and testing. The figure shows randomly selected results, and our best network does a very good job in many cases of picking up the details of the segmentation, with some minor exceptions. Next, we reconstructed a 3D model by applying the network to each slice individually and stacking the results. This is the volume for which we achieved the best results, and you can see that visually there is little to distinguish between the manually labeled segmentation and our prediction. It is also worth mentioning that no post-processing was applied here, so this is directly the output of the network. In contrast, this was the volume that performed worst in terms of the evaluation metrics. But you can see on the left that in this case the blood vessels have not been segmented by the radiologist, so there is a slight inconsistency in the dataset, as most of the training volumes do include blood vessel segmentation. So this explains the low score, at least to some extent. Finally, just a quick comparison between the different networks and also a state-of-the-art dense VNet on this dataset. You can see that the unet implicit performs significantly better than the VGG-inspired networks, but that the improvement comes at the cost of the size of the network as well as the inference time. The performance of unet implicit should be considered on par with the state-of-the-art dense VNet, especially given that our results applied no data augmentation and that we discarded some superior training runs in order to maintain consistency. To conclude, I would like to point out that the method is generic and can be applied to other reconstruction problems as well. For instance, we have also applied the method to photos taken during the 3D printing process. The image shows a 3D model of a rocket engine part printed at Additive Industries in the Netherlands and reconstructed with high accuracy from the image data. We are looking forward to applying the method to other reconstruction problems as well. Thank you for your attention.